early universe. Something was hiding in the dark. Something massive, ancient, impossibly heavy. A black hole millions of times the mass of our sun, already enormous. And it existed when the universe was barely a newborn. According to the models we trusted for decades, it did not have enough time to form. It should not have been there at all. Pause. And yet, when we finally built an eye powerful enough to look, there it was, waiting for us in the first light of the universe. This is the story of the black holes that should not exist. For a long time, we believed we understood how black holes grow. They begin small. They feed slowly. They take billions of years to become giants. That was the rule. That was the timeline. And it made sense. Pause. Then, in 2022, we switched on a new kind of eye. The James Webb Space Telescope. It sees in infrared, the kind of light our own eyes cannot. It can gather light that has traveled for more than 13 billion years. Light from the very first galaxies, from the edge of the beginning. When Webb turned toward the dawn of time, astronomers expected to find faint, simple, half-formed objects, the awkward infancy of the cosmos. That is not what they found. They found giants, black holes already enormous when the universe was only a few 100 million years old. By the old timeline, that made no sense. And this was only the first surprise. What black holes are. To understand the mystery, you first have to understand what a black hole truly is. A black hole is a place where gravity has overwhelmed everything else. When a giant star runs out of fuel, its core can collapse, falling inward into a space smaller than we can picture. Around it forms a boundary called the event horizon. Cross that line, and nothing returns. Not matter, not light, nothing. That is why they are black. They swallow their own light and give nothing back. At the very center, our current equations point to something called a singularity. But here, we have to be honest. That center is not really a place we understand. It is a place where our physics stops working. It is less an answer, and more the edge of everything we know. The largest of these objects, the supermassive black holes, sit at the hearts of galaxies. Our own Milky Way holds 4 million times the mass of the Sun. And normally, growing a monster like that should take an enormous amount of time. Why early black holes are strange. Here is the heart of the problem. A black hole grows by feeding. It pulls in gas, dust, and anything that wanders too close, slowly getting heavier. But there is a limit to how fast it can eat. As matter falls in, it heats up and shines with tremendous force. That radiation pushes the surrounding gas away, like a gale blowing back against its own meal. Scientists call this the Eddington limit. Feeding at that safe pace, growing into a supermassive giant, should take close to 1 billion years, perhaps longer. But the black holes Webb found were already giants far earlier than that. One of the most distant confirmed examples existed just 570 million years after the Big Bang. Then, in 2025, astronomers reported an even more distant one, in a galaxy called Kuiper's LRDZ9, present only about 500 million years after the beginning. The problem was not just distance, it was timing. There simply was not enough of it. Imagine finding an ancient, towering tree in soil that was only planted last week. The tree is real. You can touch it. But the timeline makes no sense. That is exactly the problem these black holes created. To grow so massive, so fast from a tiny seed, they would have had to feed without pause, at the very edge of what physics allows for the entire history of the young universe. And even then, for the biggest ones, the math falls short. Something was wrong with the story. And that is where the old model began to crack. Next, you have to understand what Webb is actually seeing. When we look far into space, we are also looking far back in time. The light from these ancient objects has been traveling for billions of years, and along the way, it has been stretched. As the universe expands, it stretches the light crossing it, pulling it toward the red end of the spectrum. The farther away something is, the more its light is stretched, and the redder it appears. Scientists call this redshift. It is one of the ways we measure the distance and the age of the cosmos. So the earliest objects glow with a deep, ancient red. And scattered across Webb's images of the early universe, astronomers began finding strange little smudges of exactly that color. They named them the little red dots. At first, they were baffling. There were far more of them than anyone predicted. They were too small and too compact to be normal galaxies. They gave off almost no X-rays, which was strange, because feeding black holes often blaze in X-ray light. Every explanation solved one piece of the puzzle and broke another. Some looked like tiny galaxies. Some looked like something we had never catalogued before. But many of them shared one quiet, unsettling detail. Deep in their light were the fingerprints of gas moving at tremendous speed, whipping around at hundreds of kilometers every second. Gas moves like that when it is trapped in the grip of something powerful. Something with immense gravity pulling it into a tight, violent orbit. A growing, feeding, supermassive black hole. So these faint red smudges, scattered by the hundreds across the early universe, may not be simple young galaxies at all. They may be the hiding places of the very giants we were trying to explain. And that is where the mystery began to deepen. Science does not move in a straight line. It stumbles. It corrects itself. And that is exactly its strength. Consider a black hole called LID 568. When it was first studied, it appeared to be feeding at an astonishing rate, around 40 times faster than the Eddington limit should ever allow. It looked like a black hole tearing up the laws of physics. But then astronomers looked again. They found that thick dust had distorted the original measurements. Once that dust was accounted for, the feeding rate dropped dramatically, much closer to the normal limit. It was a warning. In the early universe, dust and distance can fool even our best instruments. And in January of 2026, a larger study went further. Looking at a group of these little red dots, researchers found that black holes may be around 100 times less massive than earlier estimates had suggested. One discovery made the mystery smaller, but the core problem did not disappear. Even after these corrections, the earliest black holes were still too large too soon for the old slow-growth models to comfortably explain. The numbers still did not fully work. Light seeds, heavy seeds, and super Eddington feeding. So how do you build a giant so early? Every black hole begins from a seed. And there are two competing ideas about what those seeds were. The first is the light seed. In this picture, the seed is a dead star, small, only dozens of times the mass of the sun. To become a supermassive giant, it must grow for a very long time. The problem is obvious. In the early universe, there was not a very long time, unless the feeding rules can bend. One possible explanation is called super Eddington accretion. Recent simulations suggest that in the dense, gas-rich hearts of the first galaxies, black holes may have gone through short, violent growth spurts, brief windows where they fed faster than the normal limit, and somehow got away with it. If that is true, a light seed might still race to enormous size if the early universe was wild enough. But there is a second idea, and it is stranger. What if some seeds were never small at all? Direct collapse and the black hole star. Some scientists think that in the early universe, enormous clouds of gas may have skipped the star stage entirely. Instead of forming stars first, a giant cloud could have collapsed directly into a black hole. No slow build-up, just a vast cloud falling straight into darkness. This is called a direct collapse black hole, a heavy seed, and it could begin thousands, even hundreds of thousands of times the mass of our sun. Right from the start. Begin that big, and there is finally enough time to become the giant's Webb seas. We have not confirmed this yet. It remains one possible explanation among several. But in 2026, we got a rare and haunting clue. Studying a later little red dot known as Glimpse 17775, astronomers used the natural magnifying lens of a galaxy cluster to gather the deepest spectrum ever taken of such an object. More than 40 separate lines of evidence pointed to the same picture, a rapidly feeding black hole wrapped inside a thick glowing cocoon of gas. Scientists gave it a name that sounds like poetry, a black hole star. It may be a snapshot of a black hole caught in the act of growing up, still buried in the gas of its birth. Did black holes build the first galaxies? Now think about what all of this might mean. For decades, we believed galaxies formed first, and their black holes grew slowly inside them, like a heart forming within a body. Galaxy first, black hole later. That was the order. Pause. But in 2026, Webb studied a tiny distant object called QS01, seen as it was about 700 million years after the Big Bang. At its center sat a black hole of roughly 50 million times the mass of our sun. And here is the part that stunned astronomers. That single black hole made up around 2/3 of the entire object's mass. There was very little evidence of a normal mature galaxy around it. The gas was nearly pure hydrogen and helium, barely touched by the heavier elements that stars create. Pause. In our galaxy today, the central black hole is a tiny fraction of everything around it. But in QS01, the black hole was almost the whole thing. Scientists think this may mean the black hole came first, that it may have formed before its galaxy, not within it. The universe had built the monster before the city around it was finished. If that holds true, then these dark giants were never just passengers riding inside galaxies. They may have been the seeds those galaxies grew around, part of the architecture of the cosmos itself, perhaps even part of the story of our own. We live on a small world, orbiting an ordinary star, in a quiet arm of one galaxy among trillions. And yet, from here, we built a machine that can stare back almost to the beginning of everything. We looked into the first light of the universe, and we found giants that our rules said should not be there. But maybe that was never the right word. They were not truly impossible. The universe clearly made them. They were only impossible to explain, with the theories we carried, and each one we find forces us to grow, to ask better questions, to admit how much of the cosmos still lies beyond us. The giants were never impossible. They were only impossible to explain. And somewhere, in the first darkness of the universe, more of them are still waiting.